Okay. You don't have to write any of this down, and I'm going to tell you right off. This is not going to be assessed. We're going to do a couple problems together, and we're going to call it a day. I just want you to have seen this before. So every bit of motion, and we talked about this when we started two-dimensional motion, is relative to a frame of motion. Relative to the floor in this room, I am standing still. Relative to the earth, I am standing still. Relative to the sun, I am hurtling at an alarming rate of speed through space. So that's that whole idea of frame of reference. Anybody here been on a hayride? Excellent. Or ridden in a vehicle? Okay, good. You've all ridden in vehicles. Excellent. If not, I would have to assign homework. When you are riding in a vehicle and you're belted into the front seat, your motion relative to the vehicle is 0. Your butt's planted on the seat, you're strapped in, your motion relative to the vehicle itself is 0. However, your motion relative to the earth is, 70, 100, 115 kilometers per hour. That's relative motion in a nutshell. If you're, and the example, a car blows past you and you're standing still on the sidewalk. Their motion relative to you is going to be what's reflected on their speedometer. Now, of course, our speedometers don't say north, south, 40 degrees south of west. But if you're driving up the highway, and I had this experience the other day, I was doing the speed limit, which is 70 miles per hour on the turnpike, 115 kilometers per hour, and somebody pulled past me, and I swear it looked like I was sitting still. Like they blew past me and just kept pulling away. I thought, dear God, that person's got to be going like 100 miles an hour. I mean, just insane, stupid rates of speed. That's relative motion. To me, it looked as though they were going about 30 miles an hour because they were probably going about 30 miles an hour faster than I was. That's relative motion. And when we do relative motion problems, we're always thinking in terms of these stupid little subscripts. So I'm going to say velocity of Moser's car with regards to the earth. So that was me. Let's see, can I draw my little car? There. That's not bad. There's the antenna. We're better off without the antenna. Okay, so there's Impy. That 110 kilometers per hour east is my velocity with regards to the earth. If that other car, I think it was actually a pickup truck, passes me, and their velocity, so we'll say other car, let's see, we'll say velocity of the stranger with regards to the earth is 150 kilometers per hour east. How do we find the velocity of the other car with regards to me? And this is where I hate relative motion. Students hate relative motion. I want you to have at least attempted to wrap your brain around it once. There are no cut and dry formulas for this. You just kind of figure it out. Each time it's a little different. Ugh. And some of them are really intuitively obvious and some of them are horrible. So, it makes for a great time. Let's use a couple small equations for this. So what we want is velocity of the stranger's car with regard to Moser. Well, that's equal to velocity of the stranger's car, stranger's car relative to the earth, plus the velocity, this is where it gets weird, of the earth with regard to Moser. Huh? If you're in a car and you're going 110 kilometers towards the east, and you look at a fixed object planted on the earth outside your car, it appears to be going backwards at your velocity. So this is just the negative of that. If you see, in the good old days, we were allowed to ride in the back of station wagons completely untethered to anything. It was great. You could like sit in the back of the station wagon like a puppy and stick your face on the glass and watch cars behind you. That's totally not safe. But many of us survived. Not all, but many. You've sat in the back of a bus, perhaps, and looked out the back window of the bus and seen objects just recede into the distance. That's what we're talking about. The stop sign that you're pulling away from. The stop sign is standing here in proxy for the Earth. Its velocity with regard to your vehicle is the negative of your vehicle's velocity with regard to it. So this is what we end up with. What's the velocity of the stranger with regard to my car? 40 kilometers per hour. They're blowing past me. Does this make sense? Okay. Now, the fun ones are things like if you are on a bus that is driving at 10 kilometers per hour north and you throw a softball at 10 kilometers per hour south, what is the velocity of the softball relative to the Earth? 0. Relative to a point on the planet, it's just kind of hovering there in the air, which is really cool, except we all know about projectile motion and gravity, so it doesn't stay there for long. So it's only exciting for like a little hundredth of a second or so. That's all we're going to do. We're not even going to do any problems. I just wanted you to have some sense of this. We can get into more complicated ones, which we're not going to. You know, if you have a bus moving forward at some velocity, and you cross from one seat to another, what's your velocity relative to the Earth? And you get into angles and vector addition, and it starts to look a lot like non-perpendicular vectors. And we're just not going to go there. So the rest of the time is yours to work on catapult, ping pong launcher stuff, and that's what we got. Questions?